Hello, and welcome to the Severe Thunderstorm Forecasting Example for Squall Lines. I am Joseph Patton, and I'll be your guide today. And don't forget to check us out on weatheracademy.org for learning more about how to forecast the weather. Recall the forecast cone, which gets its shape from going from broader, more general time and spatial scales to more detailed, smaller time and spatial scales as we get closer to the event. More details will be resolved, giving us more information about how, when, and where severe weather will occur. Also recall the ingredients-based forecasting method, which looks for our four main ingredients: shear, lift, instability, and moisture, or SLIM for short. With shear, we want winds to increase and change direction with height. Veering winds, or winds that turn clockwise with height, are generally better for severe weather. In addition, we need some sort of initial lifting mechanism, like a surface-based cold front or warm front or some other boundary, which will generate our initial lift for our thunderstorms. We need some sort of instability where our air parcels are warmer than their environment, and once they're lifted by that initial lifting mechanism or low-level boundary, they will want to continue to rise. And finally, we also need some component of moisture so that clouds and precipitation form once that unstable air is rising. Any other considerations may include jet streak dynamics, so the location and timing of the strong jet stream or strong upper level winds may have an effect on how severe weather develops through the event, and also any remnant surface boundaries may also affect how weather develops through the event. Starting with our first ingredient, or shear, in our upper level flow, here is an observed 250 millibar map which shows winds and streamlines across the United States. We can notice that there is a strong jet stream across much of the northern United States, and the jet streak, or blue shading, shows us that there's an area of pronounced stronger winds across the northeast United States and even dipping down into the mid-Atlantic. So this jet streak is going to provide increased upper level support for divergence aloft and increased upper level support for rising motion, which will turn into our strong updrafts and our thunderstorms. So this red oval here highlights the location of our right entrance region of the jet. Air is flowing from west to east. And this right entrance region is going to be the preferred area of upper level support, where we've got not only strong upper level or strong deep layer shear, but we've also got this dynamic support from the jet streak in our right entrance region for lift. Moving on to our second ingredient, or lift, here is a surface analysis from WPC on the evening in question. We can see that there's a series of cold and warm fronts draped across the Midwest and Mid-Atlantic of the United States. And this is going to be our boundary, which is going to be providing our lifting mechanism for the potential for severe weather on this day. Recall that our upper level support with the jet streak was generally in this area. So we've got our upper level support at the jet streak, we've got our surface-based boundary providing lift, and in addition we can see that this boundary is roughly oriented east to west, so that's going to be important later for determining convective mode. Finally, one other thing to point out here is that we've got very warm, moist air occurring on the south side of these fronts. We have some dew point temperatures reaching up into the lower 70s. We've got a 71 here. And we've got either light and variable or generally southerly wind kind of bringing up this moisture into this area. And this is being fed off both the Atlantic Ocean and the Gulf of Mexico. And this warm, moist, rich air, we see a 106 degrees here, a 97 degrees Fahrenheit here. This is going to be very unstable air, which is going to be feeding in energy into our severe weather event and increasing the likelihood of severe weather. We had just mentioned Instability. So moving on to the instability situation. We can measure that instability by convective available potential energy, or CAPE, which is plotted here in the red contours. The most important thing to note is that where we've got our confluence of both a lifting mechanism and upper level support in terms of shear on our jet streak, we have these very high CAPE values on the order of 5,000 to even 6,000 joules per kilogram. And that's going to indicate that the air there is very unstable, like we talked about. In addition, notice how there's very little blue shading in this area. So there's very little convective inhibition, meaning that there's not much to stop our storms. Once the lifting mechanism provides that lift, they're going to want to keep rising. That air is going to want to keep rising, and our storms are going to keep getting stronger. Very quickly, moving on to our moisture and our low-level analysis, we can see that there's higher low-level moisture in the Midwest and Mid-Atlantic regions, shown by these green contours, which indicate higher dew point temperatures. So therefore, we know that there's a lot of moisture in this area, and our storms are going to condense very quickly, and we know that there is a potential for severe weather. Here is an observed sounding from 18Z, so in the early afternoon or right around local noon from Wilmington, Ohio, which is in southwest Ohio. This sounding shows several things which indicate that there could be severe weather. One of the biggest one is that we've got CAPE values higher than 6,000 joules per kilogram. So CAPE is our measure of instability. CAPE is our measure of how warm or how buoyant the air parcel is compared to its environment. Our projected air parcel is going to be following this dashed dark red line as it rises, and for every point that it's warmer than the solid red line, which is the measured environmental temperature, this is all going to be upward motion. It's all going to be buoyant because our air parcel is warmer than our environment throughout this whole layer of the atmosphere. So that's basically what CAPE is measuring, is this hatched area of how unstable the air is and how much energy there is to continue to cause air parcels to rise and strengthen your updrafts, which leads to strong severe weather. The winds are slightly varying with height, but we notice we come back a little bit, and so the winds turn clockwise slightly, but if we look at the photograph, we can see it's pretty messy, so that we don't have that nice clean veering or clockwise profile with height that we would expect for more discrete convection or more supercell type convection, which could lead to tornadoes. So we've got a lot of instability, but we don't have a tornadic-like wind profile. We do have good shear. We've got strong winds. We've got just about 600 millibars. We've got 40 knots. These four long bars mean 40 knots of wind shear. In addition, we have lapse rates here in the lower left-hand corner. Very favorable lapse rates. Surface to 3 kilometers above ground level is 8.3 degrees Celsius per kilometer. And we've even got some approaching 9 degrees Celsius per kilometer in the mid-level, 700 to 500 millibars. So that means that our atmosphere is cooling, the environmental temperature, the solid red line is cooling quickly with height, meaning that there's even more area, even more buoyancy for our air parcel, which is now that much warmer than the environment, to continue lifting. Our LCL, or lifted condensation levels, is basically at the altitude at which the cloud will start condensing into water, liquid water, and we notice that our LCL heights are all well above a kilometer. Our surface-based parcel is going to have an LCL height of almost 1,500 meters, or 1,406 meters, and this LCL height is probably a little too high to expect tornadoes. But that means that this could be more of a damaging wind event than a tornado event. In addition, our deep layer shear is roughly about 285 degrees, or from the west-northwest. So our shear is coming through like this, And remember, our lifting mechanism, our surface boundary, was roughly oriented uh, west to east. So that means most of our deep layer shear is going to be parallel or right along our lifting mechanism, which is going to lead to mostly linear convection as opposed to discrete convection. So we're probably looking at a strong line of convection occurring in this environment, which is very unstable and will probably lead to damaging winds. Putting it all together, the Storm Prediction Center, or SPC, issued a moderate risk, so a level 3 out of 4 risk for severe thunderstorms on this day in the Midwest and Mid-Atlantic. And later in the day, they did update the moderate risk to include much of the coastal areas, including the DC and Richmond areas for this moderate risk, as strong winds continue to progress due to a squall line, a line of strong thunderstorms occurring in this area. And next we will look at the reports of damage from this area due to these strong winds. Here are the preliminary reports of damage due to severe weather from the Storm Prediction Center. We can see a large swath of mostly strong wind reports. That's what the blue dots and squares mean, extending from as far west as Iowa and Illinois, and then really ramping up into Indiana, Ohio, West Virginia, and the mid-Atlantic states from North Carolina to New Jersey. These represent a very strong, mostly straight line wind event where damaging winds from a line of thunderstorms, a squall line, caused wind damage over a very large area. And when we get this kind of squall line that meets this criteria for having a large area and some other dynamic properties, we can classify it as a derecho. So in fact, with this derecho, we had dozens of reports of high winds with these black squares. And the black squares on this map indicate areas where there were measured winds above 75 miles per hour. So that's great enough to cause property damage and be damaging to people and uh, and other living beings outside. So this is important for us to understand because this kind of squall line can be just as dangerous as some of the weaker tornadoes, and it can occur over a much larger area. Finally, we'll look here at what the radar mosaic showed for this day in June 2012. If we focus our attention on the Midwest and Mid-Atlantic, we can see that a large, very strong line of thunderstorms developed and moved eastward along the boundary that was providing our lifting mechanism. This deadly, damaging derecho across the Mid-Atlantic and Midwest United States resulted in, unfortunately, 22 fatalities and nearly $3 billion in damage. So this radar shows where that derecho occurred, and we know that the measured wind gusts were up to 91 miles per hour. So understanding the environments in which these kinds of severe weather events can occur can help keep people informed and safe, and they will know that they should seek shelter when the environment is primed for severe weather, and so should you. So thank you for listening to this lesson. Stay tuned for more courses on meteorology with us at weatheracademy.org.